We're very pleased to welcome Peter Onyisi from the University of Texas at Austin to be the first colloquium coming from an outside person in a long time. So welcome, Peter. I think we overlapped first in around 2003, 2004 when you arrived at Cornell to do your graduate work, and I was there at the time. Peter had come from University of Chicago, and he returned to University of Chicago, so he went on to continue research in particle physics from working on the Clio experiment at Cornell, and then I think also at Chicago for a bit, and also joined the ATLAS experiment. And I think today we'll hear more about his adventures on ATLAS. Among the physics options that he's interested in, he also works on the large data sample, so computing and how to reduce these data sets to tractable things that we can learn about the world from. So he may be mostly telling us about the top Quark today, but he knows a lot else about how ATLAS manages to get their data processed. So thanks, Peter, and we're looking forward to your talk.
Thanks, Carl. And I have to say, it's it's really great to actually be able to see people not from my institution in person. So thanks for having me. And I've had a great day so far. I was expecting, all the stories of the annoying young grad students. So, I don't know, you can tell people in private. Okay, so I actually made a little bit of a change in the title. So you're getting top Quarks, the new flavor, tying it back actually to sort of what I was doing as a grad student, because apparently once you start flavor physics, you can never really escape. So I'll tell you what that means, what I mean by flavor physics, and the fact that I would argue that I'm still doing it, and why that's interesting for us to pursue at the Large Hadron Collider, specifically with top Quarks. So I'm going to give you a sort of very whirlwind introduction to what sorts of things we're interested in particle physics and flavor physics specifically, starting with this little diagram where we can imagine, pursuing physics studies in one of two directions. One is going, down, smaller and smaller, trying to understand the fundamental constituents of matter to the point, you're going from visible stuff to understanding that it's made of different kinds of elements, which are fundamentally atoms of different kinds. Those atoms are composed of electrons and nuclei, and different numbers of electrons give you different chemistry. The nuclei determine how many electrons you have. The kind of nucleus you have is determined by the kinds of protons and numbers of protons and neutrons you have in that. And then the fact that you've got these protons and neutrons and a whole bunch of other kinds of similar particles of that kind are determined, the kinds that you have are determined by their constituents, quarks. And in this diagram, I've shown, these are the fundamental kinds of matter that we know that make up our everyday life, the electrons in atoms, and then the quarks composing the protons. And I should, of course, say, these things don't just, orbit nuclei on their own. They're held in place by fundamental forces, in this case, electromagnetism, in this case, a strong force. So it's not just the kinds of matter you have that's important, but what interactions they have, what forces they feel, how strong those forces are, and what regimes they come into play. Of course, this would be a very, if I just said the whole point of what we're trying to do is to go in that direction, that would be leaving out an extraordinarily rich world of trying to understand how you go in the other direction, because even from going from, as people here are very well aware, just to go from the quarks to explain the structure of protons is a very, very difficult task that has no analytical solution, and some of the most powerful computers in the world work on this problem a lot. So going from trying to understand the emergent phenomena that come from fundamental objects and then their interactions is incredibly important in making sure that we actually do have the correct underlying picture. So I can summarize in terms of all the directly observed particles in this. We used to arrange things in kind of a periodic table format. And then I guess graphic designers thought, let's emphasize the centrality of this great Higgs boson thing. So they changed it to this pie chart. So we have a list of all the directly observed particles. And then, as I said, it's not enough just to know what that list is, but you also want to know the rules that govern their interactions. And in principle, you can stick it onto this coffee mug, which sort of famously actually has a double counting in it accidentally. So actually, I think they corrected that in later printings of this. So we have in this pie chart, and I'll go through in a bit, we've got on the outer ring the particles of matter, in the middle ring the force carriers, and in the middle the Higgs boson. So all ordinary matter, the stuff that we interact with on a day-to-day basis, is made of just three things in this pie. And you could be forgiven for asking why the rest of it is necessary. And then the question, why is the rest of this interesting and necessary, is basically flavor physics. So these electron and the up and down quarks that make up ordinary matter, the up and down quarks make up protons and neutrons. These have heavier siblings. So for example, the electron has these heavier relatives, muons and taus, which have the same fundamental charges. They interact with forces the same way. They have different masses, though. Same with up and its relatives charm and top, and I'll be coming back to this one, and down and the relatives strange and bottom. And so, of course, this question here, who ordered that, uttered when the muon was first really isolated, still applies today. No one really knows why there should be three generations. So yeah, so this pattern of having triplicate is called having three generations. There are also neutrinos, which are actually extremely, there are an enormous number of them. 100 trillion neutrinos from the sun pass through you every second, so just number-wise, they're just all over the place, but since they interact with you incredibly rarely, it wasn't until the 20th century that we actually saw them. So here's a kind of a detector that would be used to detect neutrinos, and here are people on the float in this water and basically accumulate enormous amounts of material in the hopes that these very rarely interacting particles will occasionally interact with them. But you can do things with a neutrino detector, such as see the sun through the Earth, because generally the neutrinos, you're looking for neutrinos that manage to pass essentially all the way through the Earth and then manage to give out in your detector. So moving on from the matter particles, we have the particle of light, of electromagnetism, the photons, that keeps electrons in atoms. It's what makes chemical elements what they are, that and the Pauli exclusion principle, basically. And that's, the entire range of, in fact, basically human interactions with the world, because we're very visual beings, are mediated through this fundamental force. Our eyes are photon detectors, after all. We have the gluon. This is the thing that actually makes protons and neutrons possible. They binds the quarks into small components. And then the W and Z, which are the particles of the weak nuclear force, best known for mediating radioactive beta decay, allowing the sun to shine, allowing the sun to turn 4 hydrogen nuclei into a charge 2 particle instead of a charge 4-1 by turning protons into neutrons, so allowing fusion to occur in the sun. And then the Higgs boson, which again is put in the center here, giving mass to all the other particles that have mass in this picture. So the photon and the gluon don't have mass, but everything else is interacting. So that's the spectrum of particles we have. What is this actually, in terms of the coffee mug, what are we talking about? So we can isolate these different parts. So we have the motion of the force particles, photons, gluons, W and Z, which is very just sort of abbreviated very quickly in this. Then we have matter particle motion and interaction with the forces, which is actually forced under very, very strict mathematical symmetry principles as to what kinds of interactions they can have. So in fact, that's one of the great accomplishments of 20th century particle physics, was understanding and uncovering this very deep structure of symmetry that predicts what kinds of interactions can occur. There's matter-particle interactions with the Higgs field, which, unlike this term here, which has an enormous amount of forced symmetry built into it, it's not exactly random numbers, we don't think, but we don't know where the coefficients here come from. And there are a lot of them, so this is, and then we have terms involving the Higgs field motion itself and its interaction with forces, and how the Higgs field interacts with itself. So when I talk, this is our nice abbreviation for what's going on. If I were to actually write out all the terms, it looks more, okay, this is a slightly aggressive writing out of all the terms, but But you get the picture anyway. In terms of the actual model for how the Higgs is giving masses to things, so we would go back to this famous paper by Steve Weinberg, which in a very real sense we've all just been elaborating on since 1967. Where actually at that point, this was written in terms of, it's called a model of leptons, because at that point, we knew what leptons were. Quarks were kind of this, so I think at that point it was weird, possibly mathematical fiction kind of thing. Actually, I don't know if they'd really even gotten to that point. But at that, we knew that there were electrons and muons, so Steve could write this thing. As I said, basically, we've been chasing ever since. So the picture I've given is very nice. For everything that we've been able to, well, okay, for almost everything that we've been able to measure, for everything that we can really make good, precise determinations of, the picture works extremely well. However, there are clear holes in it. There's no gravity in this picture, so obviously I'm standing on this podium. I'm not floating in the air. It's not electromagnetism keeping me there. So we have no verified theory of quantum gravity, how to incorporate that in this. We don't have neutrino masses directly in this picture. So it's in any case, however you want to resolve the question of how neutrinos have mass, in principle, you could just give neutrinos masses the same way the other matter particles do by having them have very weak interactions with Higgs boson. But that, in any case, requires particles that are degrees of freedom, as we'd say, that are not in the standard model. It requires an extension. We know that, in fact, the dominant form of matter in the universe is not ours. At least if you look at the way the universe is clumped in the early universe and how it expands now, it's very much consistent with there being a very large component of matter that is far beyond what is the baryonic component, and we definitely see the properties of this object not being like what the standard matter is like. So we believe, of course, particle physicists, we want to reduce everything into some kind of particle if we can. So we'd say that astronomy and cosmology require some dark particle, which is not neutrinos. They don't have the proper kind of behavior. We know enough about this dark matter to say it's not neutrinos. Even worse, there's this thing called dark energy fueling an expansion an accelerating expansion of the universe that is absolutely not in this picture, or at least not in an obvious way. There's not enough matter, so if you try and figure out how much matter would be generated, assuming that the universe started off in a state of perfect matter-antimatter equality and evolved to the state of matter dominance that it has now, we know that there is a mechanism that would allow that to occur in the standard model, but not enough matter would be generated by it, so we don't know how to create enough asymmetry between matter and antimatter in this picture. And then there's kind of this technical thing which, for what it's worth, has driven an awful lot of work over the past many decades of so-called naturalness, which is basically the parameters that you have to put into the model to explain the Higgs field are highly fine-tuned in the sense that they vary dramatically according to the scale at which you probe them, and it's unclear why at sort of large scales it should have the sort of apparently very fine-tuned values you do, where you have to have extraordinary cancellations at very short scales. So what I'm going to talk about is essentially these parts of that Lagrangian. So the matter-particle motion and interaction with forces, and the matter-particle interaction with the Higgs field, mostly this part, actually. So I'm going to talk about how we look for the terms here that involve the top quark interacting with the Higgs, and also potential terms that could be there, just from, if I just took symmetry principles, I could imagine those terms might be there in a really general Lagrangian, but are not there in the specific Lagrangian of the standard model, so finding them would indicate that we had broken this picture. Actually, I might say, and this will sort of go into the next picture, if you talk to a lot of my theorist colleagues, they will say, actually, this structure as written here is extremely minimal in a sense, but you would generally expect a whole bunch of really, at higher energies, very high energy scales, very, very massive particles, much, much more massive than the sort of things we explore today at our relatively low energy scales. And those would generate additional terms on this. So you would generically expect to have a whole bunch of extra stuff tacked on to the end that's not sort of constrained under, it's not in this picture. So there's a motivation in any case to expect that this is sort of a leading order approximation to a much more complicated structure that we can go hunt for. So I just wanted to make a connection to some very early work on beta decay. So this is, it's actually I love the fact that Fermi's actually correct explanation of what was going on here was rejected by nature for being speculations too remote from reality to be of any interest. So perhaps your idea is too good for nature. So let's think about neutron decay. So let's go back and, as we do in modern physics classes, imagine yourself from the point of view of someone who knows that some nuclei change into other kinds of nuclei. Let's idealize that you actually have neutrons and you see that neutrons decay. Well, you have, in the picture without the weak interactions, without the W and Z, you have electromagnetism, you have a strong force. Neither of these things change the kinds of particles you have. So electromagnetism, I don't change a proton into a neutron by emitting a photon from it. So from that, very early point of view, I would have to say if I can change a proton into a neutron or a neutron into a proton, then there has to be some kind of new interaction going on. It's not electromagnetism, it's not gravity, it's not whatever is keeping protons and neutrons together. There's something else. So we also know that this thing has to be, because these half-life is quite long, this thing is a rare interaction, right? It's not something that proceeds at very high rates. And Fermi was able to describe this at low energy by putting in this so-called 4 fermion coupling, where you simplify it to say that I have a neutron, and then something happens, and I get a proton, electron, and an anti-electron neutrino. And that involves some coupling strength, which in this picture actually has dimensions in it. So we have some interaction whose strength has a dimension, and if you run calculations through it, that would predict interaction rates that grow actually as energy squared. It's basically to cancel this dimensionality of this coupling. And so you could very roughly estimate that something has to cause this to stop growing at the energy scale at sort of order 1 over square root that, right? So if this becomes order 1, bad things can happen. So we should expect some new physics to occur around here. And in fact, there was a direct observation of exactly that. We resolved this point interaction here into 2 different interactions. So one is a down quark becoming an up quark with an emission of this W particle, and then the W particle decaying into an electron and an anti-electron neutrino. So this is the zoom in of that point. And the point is you can actually, even though this, if I just have the neutron, it's a very low energy scale, but I can still be sensitive to the fact that this W exists by the fact that this extremely rare interaction occurs. So in 1983, the direct observation of these force carriers was observed in an event display with high-level technology from that time, the leading-edge computer graphics from UA2. So this is a prototype of what we would call today an effective field theory, and this is sort of what I was referring to by saying these, we would tend to imagine that very rare interactions that probe very, very massive particles beyond what we can directly access might be out there, introducing new kinds of structures at low energies that we can look at. So the interplay here is something like, at low energy, we see that something's going on, and at very high energy, we might see what exactly is going on here. So between low and high energy physics, by our scales, you can have this very interesting thing. But also notice the time scale of 50 years between the description of the low energy theory and the observation directly of the high energy theory. Okay, so moving to Higgs, why do we care about the Higgs? So this basic point is that masses, if you were to write out this Lagrangian term here, and you're going to write this thing here, but you said, well, let's try and do it without a Higgs boson. It turns out that we want the Lagrangian to be charge conserving, but just putting in a bare mass term violates specifically the charges of the weak force. So we want to conserve the charge of all particles under all interactions of forces, but we can't do that if we just stick mass terms directly in. So the solution is that the underlying laws are charge conserving, but the vacuum, the ground state of the world that we live in is not charge conserving. So this is a quite familiar phenomenon in many fields. This is spontaneous symmetry breaking, superconductors, ferromagnets, et cetera, which comes from some self-interaction of something that carries a charge that causes it to prefer an energy state where it's non-zero in the lowest energy configuration. So we call this the Higgs field. So we have a non-zero vacuum value. Here's a nice little depiction of it. So, you actually do have a symmetry around zero field, but it's a local maximum. And then you roll down to some point of lowest energy, which is degenerate. Okay? But the value of that vacuum expectation value sets the scale for masses of fundamental particles. And then the oscillations around that minimum give you the Higgs boson. So actually what we're discovering when we talk about the Higgs boson doesn't give mass to particles, the Higgs field does. The Higgs boson is sort of this remnant degree of freedom that tells you, that you can actually probe, which tells you something about the fundamental couplings that are going on there. So again, in an analogy with a magnet, the underlying laws that are of the material and of electromagnetism are rotationally symmetric, but the ground state in these domains is not. There is a preferred direction. And the effective laws here, if you're sensitive to magnetization, have a preferred direction. Okay, so here's some predictions the standard model makes for how the top quark and the Higgs boson interact with each other. So this is complicated as the things are going to get, and it doesn't matter whether or not this thing, you can read this, I will explain the important parts to you. So the first thing is that the interaction strength, so basically, imagine I have a top quark coming in, it emits a Higgs boson, and there's a top quark coming out. And these things, of course, we want to conserve energy and momentum, so these things are virtual, and you have to put this into a proper full diagram, but I just want to isolate this one interaction here. The strength of this is going to be proportional to the mass of the top quark. So the heavier the matter particle is, the stronger this interaction is. In fact, this interaction, this number yt, this parameter is essentially 1 in the standard model. It's an extremely large coupling. In fact, it on its own would kind of be non-perturbative. You cut it off by the fact that it's hard to make top quarks. So you expect this interaction strength to have a certain value. You also expect it to have a certain form, and when I say form, I mean essentially the angular correlations, exactly how the directions of things and the spins are related in a diagram like this. So, not to get into too many details, but there's one particular kind of interaction you can write, which we do believe that's what the standard model requires. There is something similar, which would also be a diagram like this, that there would be a top quark in, a top quark out, and a Higgs boson, but would have essentially opposite parity, which is not permitted, not expected. And this, you could have an even more complicated thing, where this actually would involve an interaction with an additional gluon. And that would be sort of a low energy approximation here. And that's absolutely, this is an example of something that would be induced by some new kind of particle that is much, much heavier than what we are actually than what we are able to directly produce. And then you also expect in the standard model that you never have an interaction where a top quark turns into a different kind of quark by emission of a Higgs boson. So in the standard model, you have this principle that other than emission of the W boson, you never change some particle into another one, definitely not with an emission of a Higgs. And here that would be violated. So an interaction like this is not permitted. So if anyone's really curious about this afterwards, we can talk about it. I'm only going to talk about, in the interest of time, only these first 2 bits, where we're going to see that, in fact, as far as we can tell, this is what's expected in the standard model, and as far as we know, we don't have structures that are not standard model-like. Okay, so there's also this thing I like to show, this doomsday plot here. So the question of the stability of the electroweak vacuum. So I said, okay, the Higgs field likes to be in this lowest energy configuration, which is not zero. So if you zoomed in very close, so this is a scale of the magnitude of Higgs field, and if you zoomed in very close here, you would see our vacuum, which is not at zero field, but is a local minimum. But then the question is, how does this effective potential, potential energy, in fact, evolve at very high values of the field? So it's actually not just the simplest thing that you get out of the standard model, because there are quantum corrections. The Higgs boson interacts, especially with the top quark, because the coupling there is essentially 1. And so you do get corrections to this potential coming from the top interactions, things like this. And that causes a change in, this is not a quartic. You do have deviations from this upward monotonic behavior. So you can wind up, and in fact, if you can wind up with a situation where you have a second local minimum, but at an energy higher than our local minimum here, in which case, okay, that's fine, we're stable, we're still in the global lowest energy state. You could have a case where, in fact, this minimum is very, very low here, much lower energy than our situation, our vacuum, in which case you would expect the possibility of a quantum tunneling event from our vacuum into that one. Now, the fact that we haven't done that yet, the fact that we are in our vacuum, indicates that that situation can't occur. Of course, if we had measured parameters that indicated that that would occur under the standard model, we'd all be rejoicing, because we would have actually direct evidence that there had to be physics that wasn't in the standard model that affected the Higgs boson. So it's a bit, so I'm spoiling the punchline here, but in fact, unfortunately, we're not in that situation. But there's an intermediate case where, in fact, there's a second minimum, lower energy than ours, so we're not in the global minimum, but the tunneling time is so long that we would, within the lifetime of the universe, it's perfectly fine, we're still here. So basically the parameters that matter here are the Higgs self-interaction, the Higgs mass, and the top interaction. I should mention the Higgs gives mass to itself, right? So, so that's how it bootstraps itself, essentially. And the top interaction, which is here, the top mass. And if you look at where we are in this plot, so you have these regions of instability, absolute stability, and metastability, where we just haven't tunneled there yet, you find that, as far as we know, we are actually in this region of metastability. So there is, in fact, a second minimum of slightly lower energy than ours, not enough to have upset the delicate balance of the universe yet. And it's okay, you have to assume some kind of measure on this space, but you would tend to think that this yellow band is a fairly small fraction. If you're just throwing darts at this, you would probably hit something else, right? So whether this picture, I mean, you can actually see here, for people who are familiar with top physics, this band here is a few, it's less than 1%, or, well, it's a percentage wide on the top mass. These are measurement uncertainties at sort of 1, 2, and 3 sigma of the top mass. Actually, the Higgs mass is a much better measure now. But you see that, we could at 3 sigma be stable. We could definitely be on this border. We could have systematic errors affecting this measurement. So this actually is basically, as I coming in from this question of whether or not the actual Yukawa coupling is the thing that's giving you the top mass. So that's another reason to chase that particular parameter. Okay, so let's turn to the experimental side of this. So to make top quarks and Higgs bosons, there have only ever been 2 accelerators, at least on Earth, that have ever had enough energy to make top quarks or Higgs bosons. Well, okay, yeah, that's correct. And essentially, all the top quarks or Higgs bosons ever made on Earth have been made at the Large Hadron Collider. So here are the 2 accelerators that have ever been able to do it. One was the Tevatron outside of Chicago. One is the LHC outside of Geneva. And this is the number of top quark pairs produced per experiment. So you see that at this point, you're actually able to do, you're not, if actually, to be honest, a lot of the top physics people at the LHC have more tops than they know what to do with. So here you can really talk, as we would say, we like to use the word factory for certain kinds of experiments and accelerators, and here you could say the LHC is a top factory. So the LHC itself, here is the outline of the ring. The thing itself is sort of 100 meters underground. Here's Geneva Airport for scale. There's Mont Blanc in the background. So I happen to work on Atlas, which is the experiment which is easy to get to by tram. Apologies to my colleagues here. So So we've got two general purpose experiments. We've got ATLAS, which is basically, all my results are from ATLAS to get ATLAS chauvinism. But CMS does essentially everything we do and often better. Our also more specialized experiments, actually, which some of really exciting results have come out from that are sort of complementary to what we can do, LHCb and ELISE, which is focused on heavy ion physics. So the key point here is to collide protons with much, much higher kinetic energy than the rest mass, convert that kinetic energy into the mass of something really heavy, and probe very high energy scales. Here is someone taking a bike right at the Swiss-French border. We actually crossed the border a couple of places. We have so far not experienced a bridge scenario here, but yeah. Anyway, you take the bike, you see there's only so many access points, and the thing is 27 kilometers around, so you don't want to walk. Here is a diagram of the ATLAS experiment, people where they shouldn't be, yeah, but to scale. So it's a really large piece of equipment. It actually makes it, if you go to visit and you have the opportunity to visit sometime, please do. And CMS also. It's actually, I would honestly say, much less visually impressive than CMS is, because the problem is it's so big it completely fills up the cavern and you only see a very small slice of it. So you basically, if you go on a tour, you're standing here and you see between here and here, and you don't see the whole rest of the gigantic thing. In fact, the core of the experiment is not super huge, but we have essentially a very large volume that allows a very long lever arm for measurements of the trajectories of particles that allow us to get precision measurements of the curvature, and that curvature lets us measure the momentum. So this is all designed with various layers of the detector, both destructive and non-destructive for various particles, to allow us to identify what kinds of particles are being produced in collisions, long-lived particles being produced, and also to precisely measure their form momentum. So the general principle of what we're doing, we collide protons. The LHC collides protons. They have very, very high kinetic energy. In the center of mass frame, that energy is possible to turn into masses of very, very high new particles. So in fact, we're actually colliding the constituents of protons, not the protons themselves. So gluons inside protons, or the quarks inside protons, or even antiquarks inside protons. There are those. And from that, we produce some particles, but say like a Higgs boson lives 10 to the minus 22 seconds. It's incredibly short-lived. We do not see a Higgs directly. Neither do we see top quarks, which are even shorter-lived. What we see is that the top quark decays into something, turns into a W and a B usually, and then that W turns into a lepton and neutrino, or two quarks, so quark-antiquark pair. And what we see is stuff that's long enough, sort of order microsecond lifetime, that we can actually watch it pass through detectors. So we look at the patterns that come out of that. So for example, here is a visual representation of a top quark CT bar event. So we've produced what we see in the detector here is the W's decaying to muon 1 to muon 1 to electron. So we see distinctive patterns here. You see this what we put it as a green bar here. On the other hand, with nothing behind it, on the muon side, we have detections in the so-called muon system, but not this green bar, for example. And then we've got these collimated sprays of particles that we call jets. And we have actually identified these as coming from the production of B quarks. And the way we can do that is because B quarks are sort of long-lived, or the hadrons that contain B quarks, I should say, are somewhat long-lived. And so we can actually see that the particles that come from their decays are displaced from the origin. So this is where the proton-proton collision happened, as reconstructed by extrapolating back all these trajectories of charged particles. And then we see a bunch of particles that seem to have come from a point that was not actually that, and that displacement is consistent with the flight of a hadron that contains a B. So we had great success with run 2, so that's 2015 to 18 of the LHC. We were able to run at the center of mass energy of 13 tera-electron volts. In fact, we had a design luminosity, the collision rate basically that can be achieved by getting lots of protons into the beam, focusing those protons so that they're colliding head-on. and so forth. At the design luminosity, we would get 8 top pairs per second. So again, that's why I started saying, here we are talking about a factory. And we routinely achieve luminosity twice design. And we're planning to still go further. So data is still being analyzed. Anyway, here's a nice plot over the various years of operation of Atlas at different energies, raising the energy when we can. And this is 2018, the highest amount of data delivered in a single year. And all the blue stuff, clearly just a lot of, well, from our standards, a lot of data to be able to work with. So we want, before doing any sort of precision measurements, we want to know that we can establish known processes well. So in fact, we have to deal, and this is sort of the curse of hadron colliders, or like in this case, proton-proton colliders, as opposed to E plus E minus, that we're dealing with an enormous dynamic range of rates for processes. So these cross-sections you should read as essentially production rates. And so here you see, here we have 10 to the 11 for proton-proton doing something, colliding and doing something, down to, essentially, I should say 10 orders of magnitude lower, because this is 1. Protons producing a pair of Z bosons. But we have predictions, these gray bands from theory for these different processes, and we have measurements at different center of mass energies that the accelerator ran at. And so you can see for these things, really, really good agreement. Of course, at some level, there's interplay between theory and experiments. So often the theoretical predictions get updated based on some, experimental input. But indeed, we have a very, very good ability to not only measure these things with high accuracy, but also to predict what the rates should be as well. And that's important because if you're trying, in essence, what we're going to try and measure a coupling between a top quark and a Higgs boson, what we're looking for is the rate of a certain kind of process, and we need to be able to know that we can normalize it correctly to some theoretical prediction for what the standard model would give. Okay, so what limits a particle physics experiment? So one is just statistics. So the question I always get is, okay, you found the Higgs boson, why aren't you done? Well, it's actually, if you're trying to do any sort of precision measurement, there are lots of things that you have to work through. One is that some things are extremely rare. And so if you don't have any examples of some process occurring, you can't really go measure it. And some things you just have to accumulate an enormous amount of data in order to get a reasonable sample of. Or some things are very common, but just really hard to distinguish from other processes that are going on, these backgrounds that we try very hard to reduce in favor of our signals. So statistics can be an issue. We need to understand our detector very well. So a lot of calibrations, we can't really, put in, we can't just run a calibration run where we stick in a bunch of Higgs bosons and see, or Z's and see that we have the correct energies measured. So a lot of things we just calibrate with other physics processes that occur in proton-proton collisions, and then we build this chain of ladders that allow us to extrapolate from things that are well known from other measurements to what we need to know. And of course, our simulations of how our detectors respond to signals is never perfect. And then finally, on the theory side, we're always working essentially with perturbation theory calculations. These are fixed order, well, they fixed order with corrections, but these inherently have truncation uncertainties in them. And there are also lots of non-perturbative effects. Again, the proton itself is a very non-perturbative object, and so exactly how often you pluck gluons from a proton is something that you go measure somewhere else, but you have to interpret in the context of certain models, and how a gluon that's emitted from a reaction turns into a spray of hadrons. That's something that is subject to a lot of model uncertainties. So these get encapsulated in models that we have to verify the quality of. So first, the top-Higgs coupling. So here, what we're looking for is, again, we have to actually satisfy energy momentum conservation. So we're looking for this particular kind of interaction here. In practice, so this, for the thing that I'm personally interested in is the production of a top-anti-top pair with an extra Higgs boson attached, which has been emitted from some top line in this diagram. And the rate of this is proportional to this coupling constant squared. So this is going, more massive the top quark, the higher this rate will be. So you're not just, okay, so these, as we said, are very unstable particles. What you're looking for, in fact, is long-lived products of their decays. So the tops we understand pretty well. There's a limited set of things they can do. Higgs bosons actually have a pretty diverse set of things they can decay into. So half the time they decay into a bottom-antibottom pair, but these are often quite difficult to pull out because proton-proton collisions produce a lot of bottom-antibottom pairs, so you've got a large background. You can produce a pair of W bosons, so that can be easier. That's actually what I worked on before I got my job. You can make tau pairs. These are leptons, so this is actually the exciting new result that I will show. There's also ZZ and diphoton, and interestingly enough, so you might say, well, photons don't have mass. Why do they interact with the Higgs boson at all? And the answer is actually this is through a loop virtual tops and W's. So in fact, here we're seeing the effects of particles that we don't actually resolve. And then there are some other modes which are, okay, mu is actually beginning to be established. These other things are so far hard to see. So how exactly the Higgs boson decays and how the top quarks decay determine how you do your search. So not going to go through all the details. Again, if you're super excited, you can ask me later, but I'm just going to show the results of 4 different ways of looking for TTH with the full run 2 data. So first is Higgs decay to 2 photons, which is very nice. Photons are really great to measure. They're single particles. They're very easily contained. They behave in a very predictable way in interactions with materials, so you know how to collect their energy. So we can calibrate those extremely well. And so you can use the 4 momentum that you measure for photons, build up a 4 momentum for the parent Higgs boson, and then you look at the rest of what's going on in the event. You look, for example, for jets from B quarks, things that are characteristic of top production, and then you make a diphoton mass spectrum. And what you find is we would definitely call this a bump. In fact, we would even statistically say it's a 4.7 sigma bump. Fine, but we would, anyway, so we consider this established an observation of TTH production in the diphoton mode. So these events here over this line here, that's your signal of TTH production. Here is an even more, even rarer channel. So you see there's not so many events here to use. Here's Higgs going to ZZ to 4 leptons. And in fact, we look for the top in this case going to an electron plus jet. So this is actually a 5 lepton event. And if you do hadron collider physics, a 5 lepton event is really not something you run into every day. So we could actually go in and look here. So here, this is a Higgs decaying. These 4 red lines are the muons that it's turned into, and then this extra green line is an electron from the top. And in fact, the signal to background on this is something like 30. So one event like this gives you quite high confidence that this is a TTH event. So it's kind of nice. This is the purest thing we can come up with. So I'm pretty confident this is TTH. And then we get something like Higgs to BB, which is a much, much messier thing. As I said, there's lots and lots of background here. So what you do is you shove this through an enormous amount of machine learning algorithms. You try to think of really clever ways of distinguishing signal and background. In the end here, you wind up finding the difference between, essentially the points as they are and the expectation, which is the histogram. If you take the ratio here, you do see start to see a deviation from that line from 1 at high towards the right of the plot, which is where we construct for the signal to be. And so that you can see here that the evidence is less striking than on these channels, but that's how this kind of thing goes. And you see that reflected in the relative errors in these things. So anyway, the process is now well established at more than 5 sigma. We have a new thing that I would like to show briefly, which is TTH H to tau tau, which is exciting for me because my student's working on it. In fact, he did most of the work. So here we have top quarks decaying to fully hadronic state, all quarks, and the tau is also decaying to quark plus neutrino. So this is not a great channel. So what you're looking for here is this red component. That's a signal on top of this background. And okay, here it's a problem of small statistics. The signal to background isn't okay, but the statistics aren't great. So this is not a great channel for an inclusive measurement. If you look for here, we basically have a 1 sigma measurement. And so I should say a plot like this, what we're looking, 1 here is agreement with the standard model. So this is the ratio of the observed rate to the standard model prediction. And you can see these other production mechanisms of the Higgs boson, pretty good agreement with 1, TTH, okay, also agreement with 1, but with very large errors. The reason we're interested in pursuing this measurement, and it'll come back in a moment, is that this is very interesting because this is a way we can actually fully reconstruct the form momentum of the Higgs boson, even with not great resolution. So this variable here that's being plotted is actually the mass of the Higgs boson. So we can actually make a peak in the signal at 125 GeV. And so we can also measure the momentum of the Higgs boson, and that turns out to be very interesting for looking at these new kinds of interactions. So here's an event display for that. The blue cones are what tau leptons look like in our detector, and the rest of these are these jets of hadrons that are produced from the top decays. So here we sort of have a TT bar pair recoiling against Higgs. I think this is the highest PT event we had. Okay, it's probably not a Higgs actually, statistically speaking, but indulge me. Okay, so we can shove all this stuff into a big fitting machinery. All these different measurements are probing different combinations of interactions of the Higgs boson. So you could say, well, let's parameterize this all in terms of straight modifications to the standard model interaction rates for various particles. And so the one I want to draw your attention to here is what is called kappa T. So this is the multiplicative factor on the standard model coupling that is implied by all the measurements that we have put together. Again, 1 is compatibility. 1 is exactly the standard model. If it's less than 1, then your coupling is smaller than the standard model. So in fact, our measurements imply is 1 with errors of sort of order 10%. So it's on the one hand, we could say this is a great success. We have established a standard model. On the other hand, there's a lot of new physics that can hide out in a few percent discrepancy on this thing. So this is not, we don't just end here and declare victory. We really want to bring this down as much as we can. Yeah, this question.
So those dark bars are the 68% confidence limit. Don't I expect something like 32% of the data to lie outside of that range?
Yeah.
Nothing lies outside of that range.
So you see, actually, if you take the compatibility with the standard model, it's 92%. So yeah, we're much. It's on the much better agreement than 50%. So it's not. I mean, some fraction of the time you will get excessively good apparent agreement, but it's at the 92% level. So it's not overly good. If this were 99.9, I would worry. Actually, you can see some of these, like, well, okay, it's sort of the same pattern, but this is a different version of the fit, and we have some things that are more in tension, I would say. Okay, so to finish up, let's talk a little bit about non-standard model interactions. So as I said, there's a very specific form of the interaction that's predicted for the top-Higgs in the standard model, but you can write other things. So for example, here's something that involves Higgs gluon and top. So you could look for look for this different structure, this different thing, sort of different angular structure in this interaction. Or you could look for modification, some additional coupling that would also couple to a gluon here. So this would be sort of another example of this 4-particle thing that would actually be induced by some high-scale physics. And one of the most prominent modifications to the actual observables, for these new interactions is generally to increase the high momentum Higgs production. So the standard model prediction in terms of Higgs PT and TTH events, standard model back here, if I had a fully CP odd interaction, this other one here, this would be the blue, and you see that very much moves the curve towards the right. Similarly for this thing here, if you look at the modification of the standard model in gray here, this term actually causes a significant excess in the tail. So essentially, again, you throw all the measurements you have, and this actually involves lots of measurements even outside of Higgs physics, because these additional operators modify not just Higgs production, but lots of top production in general. So this is the whole world of so-called effective field theory, which is a la Fermi beta decay, where you're looking for these high mass particles through modifications of interactions with low energy. And what you do is you shove in information about the momentum spectrum as well as the overall production rates. So far, this only includes 2 photon and 4 lepton, but we are hoping to get tau in there in the next round of the analysis. And so, okay, you can't really see these things very well, but again, you sort of get, so here you expect 0. So if you have a deviation from 0, that indicates some new physics coming in. And these are limits that are being set by specifically TTH production, which are quite interesting to look at. So you see the different colors are actually meaningful. You see certain colors only appear in this box, and that means that basically our main constraint on those operators is coming from TTH production. And then just quickly on the CP-odd interactions. So this is resolved in Higgs to gamma-gamma with machine learning, which is trying to distinguish CP even and CP-odd. So they do a very dedicated analysis for this one particular kind of modification to the standard model. So the standard model here is this x at 1 on the x-axis and 0 in the CP-odd interaction. And our best fit is essentially there with the 1 sigma confidence level that includes the standard model. So far, everything looks right for that. Okay, so just a very, very brief word about where we're going here. So we're currently near design energy. We ran run 2 at 13 TeV. The design energy was 14. There is some hope that, don't take it to the bank yet. There's some hope that we might get an energy bump for the next run, which is going to begin next year. So this is where we are in this long-term plan for the Large Hadron Collider, end 2021. So we got start run 3 in 22. Those in the know this is not actually the latest full planning, but never mind. So we've already surpassed the design instantaneous luminosity, but the long-term plan is to operate even higher, another factor of 3.5 to 4 times higher luminosity data rate. So the plan is to accumulate basically 20 times the current data set for studies that require really high statistics in order to deal with all the radiation issues, long-term damage to components and so forth. Also just increase the capabilities of the detectors. There are major upgrades of both the accelerator and the detectors in progress. And you can sort of read up here, this thing goes to 2040. This is actually sort of intermediate term planning in particle physics these days. If you really want to do like really long-term planning, so here are a couple of possibilities of future facilities. So there's linear colliders. So here, maybe like an electron-positron collider, which collision energy essentially is limited by how far you have in order to accelerate the particles before they collide. So that goes up sort of order 1 to 3 TeV, lower energy, but because we're colliding the electrons and positrons and not constituents of protons, we're still able to access new things. So if you want to reach very high energies with E plus E minus, this is the only way to do it. So there are programs active at different technologies at Japan and at CERN. For circular colliders, like what the LHC is, here your E plus E minus collisions are limited to about 350 GeV because you actually just get too much synchrotron radiation from forcing the electrons to be accelerating all the time as they go around the circle. But you can get high luminosity that way, much higher than you can for these linear colliders where you only use the electrons once. Here you keep recycling the electrons and positrons. So you would then hope maybe you make an electron-positron collider, then you recycle the very large tunnel that you build to put in something for proton-proton colliders, which needs some new magnet technology. And sort of CERN and China are places where this is being actively followed up. If you actually look at this particular interaction, the LHC for a long, long time is really the only place you're going to be able to do this kind of work. And even for the high luminosity stage of the LHC, there's still going to be many statistically limited topics here. So actually the HL LHC I should sort of indicate on this is this gray bar. So this is sort of a study that was done to understand the capabilities of different colliders. Smaller bars are better. So these are different scenarios of what you can do, but you can see there are only a few things that actually significantly improve on the gray bar, and those things are actually either a higher energy LHC or the 100-kilometer future circular collider. There are other things that you actually can do at different kinds of machines, though. So, if you're really interested in top mass uncertainty, that doomsday plot, you want to shrink that top mass uncertainty, you can do that by sort of a factor of 10 with these electron colliders, where that would now be dominated by theoretical uncertainties. Okay, so that's the end of the talk. Here is a park you can go to near Austin if you want in springtime. So thanks for your attention, and again, it's been very, very pleasant to be able to come and talk to you about this.